Hi everyone, welcome to another Select seminar. Today we have Giovanni de Felice, who will be talking about fusion and flow, formal protocols to reliably build photonic graph states. Please, Giovanni.
Thank you, John. I'm going to talk about some joint work with Boldy Sarpour, Lia Ye, and William Cashman. And the main motivation for this work is to try and understand and develop formal tools for to understand photonic quantum computing. And so in this slide, you can see two pictures from papers. One is the fusion-based quantum computing paper by PsiQuantum on the left, and the other one is actually a very recent paper by Nu Quantum on distributed quantum computing. And these two pictures have some similarities. So in both, we have like some, if you look, we have some kind of resource state generation happening. So some photons are generated, and then they are put into some measurements, some entangling measurements. And there's some routing going on, some delays. And similarly, on the right, you have here, this is meant to represent, actually, doesn't have to be photons, but they could represent ions, for example, or like what they call QPUs, which would be small machines where you have like, say, all-to-all connectivity, and you can perform as many circuits as you want. And then this is a way of interconnecting different modules. So you would have ions that generate photons, and then from the different modules. And then these photons go into a routing part, which puts them into some beam splitters and measurements. So we kind of have some similar ideas where we have some kind of qubits and photons playing together. So in this, so the basic idea of these architectures is that you generate some basic resource states, like some small entangled states, here represented as graph states. And then you use fusion measurements, entangling optical measurements, to basically fuse these small graph states into bigger graph states and perform an arbitrary quantum computation. So I'm going to talk about the kind of tools that we developed, kind of graphical language tools, to try and study these architectures and also develop a compilation framework for these architectures. So this is the rough plan of the talk. Feel free to interrupt me at any time. And the structure will become clearer as we go, so it's fine. All right, so first of all, we need a language to represent both qubits and photonic modes. So the ZX calculus, as everyone here knows, is a very good language to describe linear maps on qubits, and you can use it to reason about quantum circuits acting on qubits. And it's generated by two spiders, the red and the green spider. These have rewrite rules, and so they allow us, we can reason about different compositions of this diagram. And these diagrams have an interpretation as linear maps on tensor products of the space C2, which is the space of one qubit. So this is a well-understood language for qubits. For linear optics, and for, in particular, so to understand kind of processes acting on photons, we use linear optical circuits. So these are basically the simplest things you could do in a lab. So the beam splitter, the first element here is a beam splitter. It takes two modes, which would be possible positions of the photon, for example, and gives out two modes. So it has some kind of entangling operation on two modes. And then you have a phase shift, which acts on a single mode. So this here I'm saying these are linear maps on C to the n, in the sense that they are linear maps on a vector space, which is generated where the bases are the natural numbers. So here this black dot with the number n represents a basis state of the bosonic mode. A bosonic mode is the space which is just generated by all the natural numbers. So this is infinite dimension, but in all this talk and in the work that we did, we are always assuming there's a finite number of photons. So you can think of like wires, like these linear optical wires, as qubits, just that the dimension of the qubit is not fixed. So depending on how many photons end up there, you need a bigger dimension to represent what's happening. So we can encode qubits using photons, and one particular way, which is by far the most used in the literature, is the dual rail encoding. So here we have two waveguides or two modes, two possible degrees of freedom of the photon, and we define the ket 0 state to be just a photon present in the top waveguide, and the ket 1 state to be a photon present in the bottom waveguide. So graphically, we can represent this using this generator, this gray triangle, which is a linear map, that goes from one qubit to two optical modes. So here there are two, they're very close, but it's convenient to have them kind of put together, these two waveguides that represent the photon at the qubit. And so this linear map is simply mapping the ket 0 state to the state 1, 0 and the ket 1 state to the state 0, 1. So this can be represented also graphically as a kind of interface between the two graphical languages that we define. So the ZX calculus on the one hand, and linear optics. So as you can see here, if you plug in the ket 0 state into this triangle, you get 1 photon up, 0 photons down. If you plug in the ket plus state, the ket 1 state, you get 0, 1. Here I'm putting stars. The star corresponds to a scalar, is the scalar 1 over root 2 in the standard interpretation. And you need it because ZX diagrams, or like especially states and effects, are not normalized. So this would actually be square root 2 times ket 1, the diagram itself. So that's why we need to carry around these stars, especially if we want to use these diagrams to compute probabilities, as we will see. So again, this triangle has some nice properties in the sense that you can do any single qubit unitary on a qubit using the operations of linear optics. So if you just apply a phase shift on one of the waveguides, you will get a Z phase, and if you apply a beam splitter on the two waveguides, this is equivalent to doing a Hadamard gate. And it depends on the conventions you pick for your beam splitter, but up to some reordering, we can take this to be the Hadamard gate. So far, we have only described a language of linear maps, right? We have like linear maps on qubits, we have linear maps on bosonic modes, we have the dual rail encoding that interfaces them. But really what we want to talk about is quantum channels. And in order to obtain a language of channels from a language of linear maps, you do something that's called doubling, or at least in the book by Bob and Alex, is this construction of CQ maps is like of classical quantum channels is obtained in the following way. So if you have a channel that has some quantum input and some classical input and gives some quantum output and some classical output, so this represents like a quantum channel that can be controlled by some classical variables. and can output also some classical variables in the sense that there can be some measurement happening in the channel. So this is represented by a linear map, little f, here I'm denoting it, that you compose in this way. So the quantum space becomes like the tensor product, two copies of the base space, whereas the classical space is a single copy of that space. So then you can kind of so you need these Frobenius algebras to represent like the classical data in this diagram. And this cup here represents the environment which is being discarded by the channel. So some kind of loss of information that's happening within the channel. Equivalently, you can kind of, these Frobenius algebras, you can think of them as basically as a sum over all the basis elements. So they are corresponding to bases of the Hilbert space. And so you can kind of split them into a sum over all the A's and B's. A and B are like bases for this space, which could be a qubit, could be a qubit, right? And so here it says like, okay, if I have some control variable A, I do this process and then I get B in this instance. And this sum here is a mixing sum. So since I'm taking the sum of the channel itself, so of this kind of completely positive map acting on the doubled space, what this is corresponding to is like a mixing, so like a distribution over the possible values. So there is a difference between taking the superposition of little f's, so summing the little f's and then doubling is different from doubling and then doing a sum. And so the first one is a superposition sum, whereas the second is a mixing sum. So instead of this kind of big notation, we will use a kind of simpler notation of the same thing. So here we just represent the channel by the linear map, which is basically it's a family of, here this represents a family of linear maps indexed by A and B, which is basically the Krauss decomposition of the channel. So we basically extend our language with the discarding operation, which represents the environment that will be discarded. And then we have classical variables that can appear in a diagram. When they appear, it means that if they are like not underlined, so they're just normal variables, it means it's a classical variable that we can control, that we can set to any value. And if it's an underlined variable, then it means this is an output of the process that we observe after the channel happens. Okay. So here's an example. You can write this diagram is corresponds to, well, the effect ket0 or ket1, depending whether k is 0 or 1. And so, for example, in this notation, I can write this, I can split this as a sum where k takes the value 0 or k takes the value 1. And this sum is, again, a mixing sum. All the sums that we're going to be using are mixing, are like a distribution. Only that, so in this instance, you would have observed that k is 0. In this instance, you would have observed that k is 1. And similarly, you can do this for the plus basis. And then you can show some simple rules, for example, that with the dual rail encoding, you can also perform any single qubit measurement on your qubit. So with the basic linear optical ingredients. Okay, so far we've only looked at like single qubit processes, and how do you perform entangling operations in optics, in photonics? So the kind of the basic idea of was introduced by Brown and Rudolph in 2006 is to perform, and I mean also it existed before. It's like, in the sense, or like variations on this idea existed before. It was known that you can perform Bell measurements in linear optics, although these are probabilistic, so only in a certain, only with some probability they will succeed. And they will actually perform an entangling measurement, whereas with the remainder of the probability, they would fail. And so then they would give a separable effect. So type 1 fusion is described in with optics generators like this. So I guess this I haven't really introduced, but this is a polarizing beam splitter. This is a waveguide, and this is measuring the polarization of the photon. This is equivalent to the following this circuit. So you can represent the polarizing beam splitter as a bunch of swaps on these bosonic modes. And this becomes the beam splitter that you see here. And then the measurement of the polarization becomes just measuring the number of photons on the top or the bottom waveguide. So when you take this diagram and you compute its interpretation, you can rewrite this into as a ZX diagram, but it will split as a sum. I mean, you could write it as one big diagram with the double notation, but I think it's simpler to see it as a sum of two possibilities, where you have this variable S that either takes the value 0 or 1. It's the success value. And if the measurement is successful, then you have performed an entangling operation, like a 2-to-1 spider. And if it fails, then you would have performed this other operation, which, as you will see briefly, is separable because this k pi here, so this effect would copy through. And so it's not going to be an entangling operation if S is 0. So S and K here in this diagram can be defined in terms of the A and B, so the number of photons that you obtain, that you measure from your optical circuit. So the success value is just the XOR of how many photons you got in these two waveguides. And then you can get the error with a similar procedure. So the type 2 fusion was still introduced in the same paper by Rudolph and Brown. And it just corresponds to a type 1 fusion where you perform a single qubit measurement at the end. So then it kind of simplifies a bit the picture, and it gives again an entangling and a separable two possibilities. In case of success, it's entangling. In case of failure, it separates. And we can rewrite this as follows, where we have basically that we're performing a Bell measurement if S is 1, and separable projection onto the X basis for on both separately on both qubits if S is 0. So these are the two kind of introduced by in this original paper. And one of the things that we did in this paper was to try to characterize all the possible measurements that you could do that are equivalent to these fusion measurements. So in general, a destructive fusion measurement, so like a generalization of type 2 fusion, would have 3 single qubit unitaries around your basic fusion gadget. So in case of success, it's going to be entangling, and the action will depend on the choice of these 3 unitaries. And in case of success, it will be separable. And again, the same unitaries appear in the failure case. So to kind of look at this, so if we start from this picture, we want to kind of reduce and see how many free parameters do we have? Like, how can we reduce, how could we choose these U1, U2, U3 is there some redundancy of parameters? So first you kind of like, you can reduce already to 6 parameters, and then you want to start imposing some conditions. So if you look at the failure outcome of the fusion, in general case, it can be written like this, and you will see that there are 3 cases. The first case is that the angle beta I here would be 0 or pi, and you get a kind of projector onto the z basis. The second case, you get a projector onto the x basis, and otherwise you can show that you will only get like a non-unitary error. So you're interested in these 2 cases, and if you look at the action of these, the action of a fusion measurement in case of failure in these 2 cases, it behaves this way. So if we are thinking of applying the fusion measurement on graph states, then when the fusion is red, it will disconnect. So it will copy through and it will remove all the connections of the qubit to its neighbors. Whereas if it's green, it's going to keep the connectivity of the graph state intact. So for this reason, we are interested mainly in green fusion, or what we call like fusion with green failure. So we impose this condition. That's the first condition we impose. Second condition is that it's symmetric. You can avoid that condition if you want, but it simplifies a lot the math, so it's nice. And the third and most important condition is that it has Pauli error, or that it's a stabilizer. Or yeah, I don't know actually if you can say that this is a stabilizer if it satisfies this, but basically, depending on whatever the outcomes you got, you would like that the errors induced by the measurement, by the probabilistic nature of the measurements, you would like these to be Pauli errors on your input qubits. So you can show that. So what we want is that we can rewrite this diagram into a diagram of this shape, where we've pulled all the k-pi's into the inputs. So if we assume this, then we get, if we assume these 3 conditions, then we get kind of a general form, which is the following, where we have like some possible Clifford rotations. And then basically the fusion has 3 possibilities and 1 only free parameter. So you kind of, the 3 possibilities are the 3 planes with which you could measure this kind of output qubit. And alpha is a free parameter, which is the angle at which you measure. You can only measure in those 3 planes for the fusion to have Pauli error. And similarly, in the fusion case, you will always get we will always get green failure. So note that this is not really always a Clifford map, because alpha can be arbitrary. So we can actually use, for instance, fusions to perform like phase gadgets and other kind of diagonal operations in different bases. Okay, so kind of moving a bit forward in the characterization, you can also show that if you further restrict the measurement to be the single qubit measurement to be Pauli, then you will get only 2 possibilities. One is X fusion, which is exactly the type 2 fusion that I've described before. And the other one is a Y fusion, which was also used in the literature to do repeat until success CZ gates using optical gates. So in this case, we have like, we kind of recover the type 2 fusion of psi quantum, but there's also this Y fusion, which is kind of the other possibility. The Z fusion, which you would expect, is not interesting because it doesn't create any entanglement, even in the success case. So the action of these 2 fusions, if you think about it as acting on a graph state, is going to be to in the X fusion case, is going to be to merge the two nodes into one. So if you apply it to two nodes that are unmeasured, then it will like fuse them into a single node with some possible error in it. And the Y fusion instead will create an edge between the two qubits. And again, it can lead to some errors that you want to correct. Okay. So also we can use this language, right? Right now we have a language of channels. We can use it to compute probabilities of success. So in particular, if we want to compute the probability of success for the fusion measurement, we would have to look at the following diagram. Like we assume some initial state psi, qubit state, and we put it inside a fusion circuit. We assume S equals 1, so we kind of fix S equals 1, and we trace out, or we discard the output. Here, this is a kind of type 1 version of the fusion. Then you will get this diagram. And if you see, this doesn't really simplify much further because, well, it will really depend on what psi is. So the probability of success of the fusion is not some fixed value, but it will depend on the input state. So there are obviously states for which the fusion always succeeds and states for which the fusion always fails.
Giovanni, why are you allowed to decompose the SS1 case into the k equals 0, k equals 1 with equal probability? Like, is that, I mean, that's also something you don't know beforehand, right? That they have equal probability for occurring.
This decomposition with this sum over k, you're talking
Yeah.
about. So here it's the trace. So when you trace, for a classical variable, you need to sum over all the values of that variable. So if you discard a classical variable, you need to sum over all the values of that variable. And this 1/2 actually comes from the star that we had in the diagram before. So yeah, here I'm skipping some steps. There is more details
Okay.
in the paper, but the sum is basically because you're discarding the classical output, and the 1/2 is because of the stars that are in there. So the kind of the coefficients. So that's kind of it's not a probability here.
Okay. Yeah.
Okay. So in certain cases, we can actually compute the probability of success, in particular when we assume that the input state psi is some kind of graph state where we haven't discarded the qubits attached, the qubits that are being fused. So imagine like here we don't have any way of seeing the state of the photon before it gets fused. Whereas if we had, if we were able to measure those qubits separately, as in this picture, then we can rewrite this diagram, and here we get actually 1/2 as the probability of success for any state that has this form. So it's just any state here, G could be any state. And so this proof works in general, but we had to assume this, the fact that the nodes that you're fusing are unmeasured. And the scalar 1/2 comes from the hop flow in this last step. Okay, so this ends the picture of fusion measurements. And we have this language to describe channels with measurements, classical control, but it's still not powerful enough to really represent the architectures that we're interested in. If you remember at the beginning, we had these delay lines and routers. So how do we represent these? How can we construct a graphical language that also captures these processes? So there is so in order to there is a kind of It's not standard yet because it's been defined, it's been introduced in a paper in 2022 where I was a co-author, but the work was mainly done by Mario Roman and Elena Di Lavore, who have been working on streams and how to represent kind of infinite processes with string diagrams. And so here I'm going to give a simple definition of a stream process. So let's denote by X and Y. Now the objects in your, so the wires will represent not a single space, but an infinite list of spaces. So Xi and Yi. And the stream from X to Y with initial memory M0 is going to be defined by some process for now. So an action at time step 0 that takes the initial memory and the initial input and gives an initial output and a new memory. And then this memory is fed into a stream process on the tails. So this is enough to define it. Why? Because it's a recursive definition, right? So I'm defining like a stream from X to Y to be something at time step 0 and then a stream for the future. Okay. So if you keep kind of unrolling in this way, now the stream in the future will be defined by something at time step 0, which now is time step 1, and I keep unrolling. So this gives a kind of recursive definition of a stream process. And the kind of special thing about this process is that it has a memory that can feed from one time step to the next. So making this formal in terms of string diagrams is actually quite involved because it involves like coends and showing that, I mean, making these diagrams formal, but they are actually completely formal. So as an example, to define a swap between two wires, say X and Y, we can just define the swap to be the stream swap to be the swap at time step 0 and then itself, right? So this first equation is actually enough to define it, and then you could keep unrolling this. So the swap is the swap at time step 0 and then the swap. Similarly, we can define the delay. So here I'm going to use delta X to denote the sequence where we have the unit of the tensor in the first spot at the first time step. So the first output is there's no output at time step 0 from a delay line, from a delay loop. So the first thing that happens is just the input goes into the memory. And then from then on, you are just, you can define this with an initial memory to be the swap and then itself. So this delay line with an initial value is just the swap and then itself. So as you can see, the input at time step 0 gets output at time step 1, and the input at time step 1 will be output at time step 2, and so on. Okay, we can also use like these, I mean, this is a very general kind of category that you can construct out of any monoidal category. It's the kind of category of streams over stream processes over any base. So in this case, here I'm just defining a router. An example of a router is it will route the photon either on the top wire or on the bottom wire. And so in this case, I just want to define a recursive, recursive one that goes first up, then down, then up, then down. And so you can just define it to say by saying at time step 0, it goes up, time step 1, it goes down, and then it's itself in the future. And similarly, we can define spin-based emitter. So now we can kind of mixing, so the stream construction will work over any graphical language as a base. So in particular, it works over linear optics, like we've looked at so far, or over ZX diagrams as well. So in this case, for a stream of ZX diagram, we can consider this stream, which is like, well, what it represents is an atom that emits a photon at every time step. So the atom has some initial state here, and then it will emit a photon which is entangled, which has the same state as the atom. That's why I'm putting a green spider there. And here I'm putting the triangle to say this is a photon being output and not just a qubit. And then you can think of this wire coming back as, well, it's the state of the atom, where you could apply some unitary before the next time step. And then again, you emit the photon, then you apply a unitary on the atom, and so on. So this unrolling is enough to define it. So the atom will have some initial time state, then the state is copied, the photon emitted is in the same state, and then the atom stays in its state, gets applied a unitary, and then you do the same thing again, but with different unitaries if you want. Okay, so to kind of understand, well, for now, we've kind of just defined stream processes as these kind of infinite lists of things you could do, right? But we also want like formal tools to reason about them. And one of them is co-induction, and co-induction is a particularly powerful proof mechanism, which is actually quite recent. So people don't really believe it very much, or like it's hard to actually believe it. But you'll see that I hope to convince you with this proof, for example. So here we want to show that this emitter, if you first do a pi phase, bit flip on the atom, that's equivalent to flipping all the photons that it will emit in the future. So to prove this, how do we prove this? So we start with the diagram on the left, and then we apply the definition of the stream. So this is just, well, first you do pi on the atom, then you emit, and then you do this thing again, right? Then we can use some ZX rewrite to just push this pi through. And now we recognize here that this is the same diagram as of the thing we wanted to prove. So we could kind of keep going, right? And say, but this again, I can unroll, push the pi. But how do you prove this? Well, you can just use this equality in the future of the stream, which means now as a part of my proof, I use this equality here in this step. So now I replace this thing in the future with what I would like to be, and then here I recognize that this is just the unrolling of the right-hand side, and my proof is done. So it's a bit weird, right? Because I'm assuming this, I'm assuming the hypothesis in the future of the stream, but this can actually be made formal. So here I've written this. This is kind of the rule of co-induction. So co-inductive equality, which is like an observational equality, co-inductive equality between two sequences. In this case, I'm just talking about sequences. Is the biggest relation that satisfies this, which means that is the biggest R that like such that A or B is the same as the two streams are equal at time step 0. And if I assume what I want to prove, then they're equal in the future. Then they are related in the future. So there are ways, I mean, this has been studied. There's a beautiful paper by Cozen and Silva on co-induction. And it's and here the difference between the standard co-induction and what we're doing here with string diagrams, the only difference is that here the diagrams have also this memory wire, which is linking the different time steps. For normal streams that are just infinite sequences, you wouldn't have this kind of connection. And the kind of additional power that is given by this is that now you can slide things along this wire, along the memory. So you can use co-induction together with sliding, and that gives you quite a powerful language to prove things. So another thing, and this is another kind of thing that you can take from a stream. So if you have an infinite process, you can always take the nth unrolling of that process. That will be a morphism in the base category. And in this case, here I'm showing, for example, the unrollings of a general stream. So the first unroll 0 would just be what happens at time step 0. Unroll 1 would just be time step 0 and then time step 1. So here you can see that I have some initial memory to the inputs at the two different time steps, the outputs at the different time steps, the memory as an output. So the output of this unrolling is always something that goes with that goes from the inputs to the outputs to along with the memories. So similarly here with unroll twice. So I can give an inductive definition of this. Say that the unroll n plus 1 of a stream is just the unroll n of a stream composed like this, plus some swaps, which I'm not drawing here. So I guess this y0 will have to go, just like there were all these swaps in these diagrams, you should reorder the outputs, but this has all the data that you need. So this is we are representing this unrolling with a box around the stream, which just means like the stream is something in this category of streams. And then when I apply the box to it, I just get some morphism in the bottom, in the base category. So I'm sorry for those who are not so confident with categories, but what I mean by category is just a collection of processes that I can compose in sequence and in parallel here. Okay, so we can also use this. We've seen like co-induction, and co-induction is particularly nice because it doesn't have any boxes, and you can just, and it's about like infinite processes directly. Induction, you need to truncate, and you need to look at like the truncations or the unrollings after some number of time steps. So here is an example of where we need induction. If you take one of these stream emitters, spin-based emitters, that generate a photon at every time step, and then you measure in the x basis the photons that come out, you can show that this is equivalent to, well, this is like applying a green spider that then you can fuse, so you will get some outcomes AT at every time step. And then you can prove this, so you can prove that this is just a diagram in the base category. So now I don't have any more like stream here. Like this is just a diagram as a channel represented as a ZX diagram. And the proof kind of goes by the definition of the unrolling. So if I unroll n plus 1, this is the same as doing a rotation, applying a Z rotation at time step 0, and then unrolling n this. And then, so then I can now use the inductive hypothesis, and I will get this sum, and then the two things merge, and I can recognize that this is just the same as this with n plus 1. And basically what this is saying is that the probability of a particular sequence of outcomes is going to be always like star to the n. So it's basically 1/2 to the n for a particular sequence of outcomes. But if we forget, we can of course grain this channel, and we don't store the sequence of all the outcomes we got, but just the sum, the XOR after that we keep doing with this rule. Then these stars disappear, and we get just 1/2 probability of one outcome or the other. Okay, there's a bit, so this coarse graining step is also a bit something you can do with channels represented as diagrams. Okay, so now we have really all the tools to see like how is it possible that you can do universal computation with optics, because at first sight you look at this fusion measurement and it succeeds with probability 1/2. Then how can I use it to actually perform entangling operations? And mainly all of the approaches are based on some kind of repeat until success protocol, where you can try again the fusion until you get some entanglement. There are also other ways of boosting the probabilities of success of fusion measurements, which I'm not gonna be discussing here. So I can discuss. So here I'm defining this box. It's a stream, and so this is the action that it has over time, right? So at time step 0, S is 0. So this means that this will go up. So first I get photons in, and the photons go up, and you fuse them. And then you get a success outcome, and then some kind of bit outcomes. Now the success outcome at time step t will be fed back into the router value. So this is actually a switch, like an active switch that has to be that has to take the value of the success or not of the fusion. And depending on that value, it will switch, either go up or down. So as soon as S is 1, so the fusion has succeeded, it will send the next photons down. And these are going to be measured in the XY plane with some measurement angle, and you will get some outcomes. So this is the basic repeat until success scheme, which is an extension of some known schemes that were used, in particular the one that was used for what we call the Y fusion, or is used to do CZ gates repeat until success. But here we're generalizing it to an arbitrary fusion with green failure. And so we need these measurements to actually be in the XY plane and of a particular angle. And then the proof, I'm not going to go through the full, but through the full proof of what this results in. But basically the idea is, again, you use induction and you unroll this. So here what we're considering is we're putting two stream-based stream emitters. So we're spin-based emitters that generate photons that are entangled with each other in time. And then they go inside this fusion repeat until success protocol. So, and that's the first unrolling, right? So you will try to fuse them, try to fuse the emitted photons. And then if it doesn't succeed, you will emit another photon and then try to fuse them again, and so on. So then using just graphical languages, you can prove that unrolling n times this protocol has this effect. It's not that pretty, but it's actually not too ugly either. So here we have the first two cases are like where you kind of have succeeded overall. So you performed an entangling operation. This entangling operation will depend on what measurement outcomes you got in the process. And this one in particular, so this middle one is very unlikely, like it's 1 over 2 to the n plus 1, the probability of this. It's basically the case in which you've tried n times and then only the last time it succeeded. And in this case, you get a different error than in all other cases where it succeeds. And that's why there are two different diagrams, because they have different normalization factors. So yeah, when you do things with normalization, you need to be a bit careful. But so the real difference between these two diagrams is just here we have Cn and Dn that can be different. Here instead we have Cn and not Cn that are like correlated. But overall, the idea is simple. With probability 1 minus 1 over 2 to the n plus 1, you performed an entangling operation, and only with probability 1 over 2 to the n plus 1, you didn't entangle the atoms. Yeah, you can think of this is the state of each atom that is emitting photons in the process. As you can see, you have this output of the unrolling because that's the memory at time step n, which is the state of the atom in this case. Okay, then like some simple kind of corollaries of this for the X and Y fusion case is that, well, in those cases, at least the diagrams look a little bit nicer, but overall the concept is the same. So in this case, we have fused the two photons, the two nodes with probability 1 minus 1 over 2 to the n plus 1. And in this case, we've added a Hadamard edge between them. So we've performed a CZ gate. And this is the kind of what we started from, which was the repeat until success protocol of, it's Lim et al. From 2005. Okay, so now we have kind of all the ingredients and we can plug them together to look at like an example of a universal architecture based on these fusion measurements. So in this architecture, you can see this is a very simple architecture which is universal. I don't think it is fault tolerant because it might keep photons in delay lines for very long. But in general, like it gives a nice picture of the computation. You can see there's two feedback loops in this diagram. And the first feedback loop is just the state of some atom where you can apply some unitary at every time step and you can emit a photon at every time step. This photon is then dual rail encoded into two possible modes. And this in the middle is a router that decides where the photons go. So it can depend at every time step. It may do a different permutation. So if it goes on the top part here, it gets delayed by some amount of time. What I haven't shown you is how you can use routers and delay lines to actually perform any reordering of time bins. So any reordering of the photons in their time dimension. But I think it's simple to believe that by routing them in different delay lines, you can reorder the photons at will. So here you will get some photons in delay lines that wait, and then when they come out, they either go inside a fusion or a single qubit measurement. And the fusion has to be repeat until success. So the way you route these photons, you need to send them. You need to send a certain number n of them for every fusion that you want to attempt, where you fix the n, or the number of times you repeat the fusion. And in this case, and then you do single qubit measurements on the photons. And this module just before is the correction. So what we've kind of shown is that this architecture is universal. And one interesting feature is the fact that this correction only has to be performed on the single qubit measurement, before the single qubit measurement. So the fusion, you just do it, and then you store the outcomes, and you might use them here, but you correct and do all the computation on the single qubit measurement only. So this is a particular unrolling of the architecture that you can see on the right. So let's say that UT is the Hadamard gate at every time step. Then you get this atom that is emitting photons at every time step. Then there's some reordering of the photons going on, which is this D sigma, with dependent on permutation sigma. There's some reordering of the photons, and then the sequence of operations. And here we've assumed that they're all successful. And in that case, you can write it down and you can verify that this architecture builds that graph state if these fusions are successful. Okay. So yeah, also to prove universality, we need to show that the outcomes of fusion measurements can be corrected with these single qubit measurements with this correction module. So and using feed forward of the measurement outcomes. And in order to do that, we had to extend the notion of flow in MBQC to also cover 2-qubit measurements, like the ones in and fusion measurements in particular. Right, so maybe I've been fast. Have I been fast? I don't know what time it is, but this is summary of what I've talked about. So first of all, so we've introduced these languages to describe optical protocols and photonic architectures with real world hardware components like delay lines, routers. And so these pictures that we had at the beginning, that we can now at least make them formal and reason about them. So this was through a language of qubits and photons and channels on qubits and photonic modes. We gave a characterization of all the correctable fusion measurements, and then we have extended graphical languages for quantum computing with streams, enabling induction and co-induction proofs in string diagrams. And finally, I haven't talked about this point, but I haven't talked much about this point, but also a contribution of the paper was to extend the notions of flow to cover also 2-qubit measurements like fusion measurements. So yeah, that's it.
Right. Thanks very much, Giovanni. Nice talk. Do we have any questions in the audience?
Hi, can you talk a bit more about the flow that you were talking about?
The flow.
Thank you.
Yes. So the flow part, maybe I have a slide now. I guess at the very beginning, these kinds of settings. So I mean the problem there was so flow is a structure on graphs that allows you to correct measurement outcomes. So it's used in MBQC. Is some kind of structure you can give on a graph state that tells you where an unwanted measurement outcome should be corrected. And we've seen that these fusion measurements and single qubit measurement have sometimes these unwanted measurement outcomes, these k-pi's that we were writing. And so in order to correct, actually, maybe this is a better picture. So this is like this entangling operation. That's here. This is fusion as an entangling operation. you get these errors k pi, and you want to propagate them in the future. So, I mean, it was a simple extension of the flow mechanism where we extended, we modeled a fusion measurement as adding a node in a graph that is measured in a particular basis. And when you look at this here, you can think of what's happening here for a fusion with green failure, Pauli error, is that if these are two nodes, the inputs are two nodes in a graph state, you're fusing them. It's here you're like adding a new node, applying some Clifford maps on the qubits, and then adding a new node connected with Hadamard's and measuring that node in an arbitrary basis. So with this concept, you can kind of extend. So if you model a fusion as just adding a node in the graph and measuring it in a particular basis, then you can take all the things that are known about single qubit measurements and carry them to this fusion setting.
Thank you.
An idea.
Thank you.
Okay, any other questions? So Giovanni, I was wondering, you say the streams allow you to write down success for try again until success protocols. Have you thought about sort of other examples of these things, like say I want to implement a gate at the kth level of the Clifford hierarchy. So I inject like a pi over 2 to the n, pi over 2 to the k phase, but I do a measurement, I might get the wrong one. If I get the wrong one, I have to do a pi to the 2k to the -1. And if I do it wrong, then do that. So I have these probabilistic choices at every point. But like the diagram keeps changing and there is a definitive endpoint. So it is not really try until success, but like there's a definitive like k layers to it. Like does something like that make sense to talk about in streams?
Yes, absolutely. Like, I mean, any kind of infinite process or repeating process where you don't want to fix an end time, I guess. I mean, with the repeat until success, also what we had to use was this unrolling, where you kind of want to cut the stream to a certain time step. In general, you can reason about the stream as an infinite process without having to cut it. One thing that we're looking at in particular is convolutional codes, and if you like, there's a lot of research going into like infinite stabilizer theory and how to kind of extend the stabilizer formalism with infinite streams of Paulis and streams of Clifford operations, and how to reason about these. And so that's one of the things that we're also looking at currently. So you can use, for instance, induction or co-induction to show how different gates commute. I think there's a lot to do with streams, but here it was used in a very basic way and for a particular purpose.
So I don't think you, maybe I missed it, but I don't think you talked about sort of future work in this area. Like, oh, what is there still to do with this photonic stuff?
Yeah, I should probably. I had it.
Yeah.
So yeah, I guess one interesting direction of extension of the theory is to look at like n-ary fusion measurements. Like we've just looked at binary fusion measurements where we have only 2 qubits as input, but there's some very interesting gates that you can do when you take n input qubits using these fusion measurements or generalizations of them. Some are called like GHZ analyzers, but I think there could be a lot of other possibilities in studying these. And also flow needs to be extended to handle like multi-qubit measurements. And that's kind of one of the directions. And then another things that we've been looking at is distributed quantum error correction. So here it's all, we haven't looked at any errors really, like we haven't looked at error correction. It was just like basically like a NISQ implementation of MBQC. But obviously, if you want to scale this architecture, you need to consider errors such as photon loss. And here we have a language that interfaces like the photonic side and the qubit side. So we want to see also how errors on the two sides can be corrected. And then this last point is about kind of what I was talking about, like how to use streams to study communication protocols and or error correction protocols. I mean, I think there's a lot of different ideas that one could have, but yeah, I mentioned the convolutional codes as an interesting application.